Baseball looks simple. A pitcher throws, a batter decides, and something happens. But every pitch leads to one question. Is it a strike or not? To answer that, we need the strike zone. It's an invisible box from the knees to the chest. When the batter is in his stance, a strike can happen in different ways. If the ball crosses the zone, if the batter swings and misses, or even if it hits foul, it's a strike. And if it doesn't, it's a ball. 4 balls, and the batter walks. 3 strikes, and he's out. But what happens next isn't random. There's something hidden behind every pitch, a pattern, a system you can't measure.
Hello everyone, imagine the final moment of a championship game. The crowd is roaring, the pitcher stands on the mound, the batter steps into the box. One pitch, one swing, one decision, everything can change. Most people see that moment as unpredictable, a battle of talent, a battle of instinct. But what if I told you that before the pitch is even thrown, mathematics can already tell us what is more likely to happen? My name is Lucas Valcarcel.
Today, I want to show you exactly that. Because before every pitch, there is a decision, and behind every decision, there is a probability. Welcome to the pitcher's algorithm.
To understand this algorithm, we first need 4 different ways of thinking about probability. But these 4 probabilities are not just mathematical definitions. In fact, every pitcher uses them, whether he realizes it or not. Let's step onto the mound for a moment. Bottom of the 9th, full count. The game is on the line. How do I decide what pitch to throw? Well, I can think about the situation in 4 different ways. First, classical probability. I look at the strike zone. If I divided it into 9 equal sections, each section is simply one possibility among 9. Pure mathematics. No history, no context. Just possibilities. Second, frequencies probability. Now I ask, what usually happens? Maybe this batter swings at almost half the pitches he sees. Maybe he struggles with the sliders. Now I am using data. Past events helping me predict the future. Now I think one step ahead. If I throw outside the zone, will he swing? If he swings, can he make contact? One event depends on another. Every decision creates the next decision. And finally, subjective probability. This one never appears in a spreadsheet. It's experience, it's instinct. Maybe I've thrown him out twice already. Maybe he's uncomfortable. Maybe I just feel confident. Can I measure that feeling? Not perfectly, but every athlete uses it every single game, and that's the interesting part.
Now, let's look at the complete system. Everything begins with a pitch. The ball can enter the strike zone or stay outside. The batter can swing or take. If he swings, he may miss, or he may make contact. If contact happens, the ball may become fair or foul. Every branch is a probability. Every probability creates a new decision. Together, they form a complete model of a baseball pitch. Now, let's zoom into the first step of the algorithm, the pitch itself. Before the ball even leaves the pitcher's hand, several variables influence the outcome. Control affects accuracy. Pitch type affects command. Not every pitch is equally easy to locate. A fastball receives a +20 adjustment because it is generally the easiest pitch to throw for a strike. A changeup receives -8, a slider receives -15, and a curveball receives -20, the largest penalty, because its movement makes it the most difficult pitch to command consistently. In other words, the more movement a pitch has, the harder it becomes to place exactly where the pitcher wants it. Spin rate affects movement, fatigue affects consistency. The count also affects strategy. With 2 strikes, pitchers often throw more aggressive pitches outside the zone, trying to get a swing and miss. For that reason, most 2-strike counts receive a -20 adjustment, but a full count, 3 balls and 2 strikes, the pitcher cannot risk a walk. That's why a 3-2 count receives a +20 adjustment, making a strike more likely. An even better height changes the size of the strike zone. These variables work together to determine one important question: how likely is this pitch to enter the strike zone? But throwing a strike is not enough. Location matters. A pitch down the middle receives a +25 adjustment because it is the easiest target to hit. A pitch near the border receives +10, and a pitch on the corner receives -5. Because it requires much greater precision. Now we arrive at the first major decision. Will the ball enter the strike zone or stay outside? The model begins with a base probability of 50%. Then it combines all the factors we have already discussed: control, pitch type, fatigue, the count, location, and batted height. For example, fatigue reduces the probability by 0.1 points for every pitch thrown. The count can either increase or decrease the probability depending on the situation. And batted height adjusts the size of the strike zone using a factor of 0.265 compared to the average strike zone height of 17.7 inches. After combining all these adjustments, the formula produces a probability that the pitch enters the strike zone. Now the decision moves from the pitcher to the batter. Should he swing or should he take the pitch? The batter has only milliseconds to decide. In our model, that decision depends on three key variables. First, zone perception. This is simply the in-zone probability calculated in the previous slide. If the pitch is more likely to be in the strike zone, the batter is more likely to swing. Second, the count. With 2 strikes, the batter enters protection mode, so we add 5 points to the swing probability because he wants to avoid striking out. And third, pitch velocity. We compare the pitch speed to 94 miles per hour, our reference velocity. The difference, 94 minus v, is multiplied by 0.5. Slower pitches increase swing probability because the batter has more time to react. Once the swing begins, another probability takes over. Will the batter make contact or miss completely? In our model, contact depends on 2 key factors. First, swing commitment. A batter who is fully committed to the swing is more likely to connect with the ball. Second, batting average. We use batting average as a measure of hitting ability. Elite hitters tend to have better mechanics and make contact more consistently. Using these variables, we calculate the probability of contact. Next, we calculate the probability that the contact results in a fair ball. Not every contact is fair, however, some balls are hit into foul territory, so once we know the fair ball probability, the remaining contact becomes foul ball probability, and whatever remains after accounting for both fair balls and foul balls becomes the probability of a whiff. Now we can calculate the probability of a strike. A strike can happen in 3 different ways. First, the batter takes a pitch in the strike zone. Second, he swings and misses. Or third, he makes contact but the ball goes foul. Our formula is probability of a strike equals take strike plus whiff plus foul. However, the values shown in the previous branches are conditional probabilities. That means they describe what happens next or after a certain decision has already occurred. For example, whiff, foul, and fair are probabilities after a swing has taken place. To obtain a final probability, we multiply the probability of reaching a branch by the probability of the outcome within that branch. In other words, final probability equal probability of reaching the branch times probability of the outcome. The same logic applies throughout the entire tree. Once we calculate the final probabilities for take strike, whiff, and foul, we add them together to obtain the overall strike probability. Now, the theory is complete, but does it actually work? Let's test it using one of the most famous matchups in modern baseball, Shohei Ohtani versus Mike Trout. Ohtani uses a slider, a pitch that sacrifices some command in exchange for movement. The pitch has a spin rate of 2,800 revolutions per minute. He has already thrown 25 pitches. Fatigue begins to appear. The count is 3-2, a full count. Ohtani chooses, not the middle, not the border, the corner. After combining all those variables, the model predicts a 54% probability that the pitch enters the strike zone and a 46% probability that it stays outside. Now, the focus shifts to Trout. What will he do? The model predicts a 62% probability of a swing and a 38% probability of taking the pitch. If Trout swings, what happens next? The model predicts a 67% probability of contact and a 33% probability of a whiff. Now we reach the final results. In the previous strike probability slide, we only focused on the outcomes that produce a strike: call strike, whiff, and foul ball. But a pitch can also end in 2 other ways: a ball or a fair ball in play. So we added those outcomes to complete the model. Now every possible result of the pitch is represented: call strike 20.5%, whiff 20.5%, foul ball 4.3%, ball 17.5%, fair ball 37.2%. Together, these outcomes add up to 100%. Every pitch must end in exactly one of them. Every result can be traced back through the tree. What looked random at first now follows a logical path, a path built from probability. And now we see the final outcomes. No arrows, no branches, only the final probabilities. The probability of a strike is 45.3%. For Ohtani, one outcome mattered most: the whiff. The model predicted a 20.5% chance of a swing and a miss, and that is exactly what happened. Mike Trout swung and missed.
At the beginning of this presentation, I asked, what if mathematics could predict what is most likely to happen before the pitch is even thrown? Now we know the answer, from the pitch to the sun, to the swing, to the contact, and finally to the outcome. What looked random at first followed a logical path, a path built from probability. Thank you very much. Play ball!